Question 32 is asking about forces on charges in a magnetic field. So we have a current in a wire which is traveling in this direction, and an electron is traveling in the same direction. Now, what we need to bear in mind is that an electron is negative. So the current, if we were to work out the current on the Fleming's left-hand rule, it would be in the opposite direction to the true value, the true direction of the electron. So it's suggesting that there's a magnetic force upon the electron because the current in the wire has created its own magnetic field. And according to the right-hand screw rule, if the current is going up in this direction, the B field is going around in a clockwise circle like this, around and under the wire. So we have the same thing happening here. So when it gets to the electron, we're just bringing this field further out. When it gets to the electron, the magnetic field at that point there is pointing down because it's getting ready to go under the wire and back up. Okay, and that's really important that you take note that the magnetic field at the point of the electron, the magnetic field is down. Okay, now we're asked for the magnetic force, which is the thrust or the thumb. Okay, the B field is your first finger. The current, which is the electron. Now, the current of the electron is going in this direction, but in Fleming's left-hand rule, it's always conventional current. So we have to reverse it. So this is the current, conventional current, and that's your second finger. So in order to find the direction of the Lorentz force, the magnetic force upon the electron, I'm going to point my first finger down. I'm going to point my second finger kind of behind me, southwest, okay, towards C, if you like. And my thumb, and I'm going to draw this in red because this is the answer. My thumb, the thrust or the force, is in this direction. So it's D. I would have said the answer is D. Okay. All right. Question 33 is similar to the previous resistor question. So, a resistor of resistance R is connected to a fully charged cell of negligible internal resistance. A constant power is dissipated and the cell discharges in time t. An identical cell is connected in series with two resistors, each of resistance R. So we've got kind of circuit 1, we've got R, and then we've got circuit 2, and we've got R and R. So in total, our total resistance is 2R. They're in series, so the resistors add. Okay, what is the power dissipated in each resistor and the time taken to discharge the cell? So this is talking about the second situation. So this table is for the second situation. Right, so if we're moving from one resistor to two resistors by the same cell, the power dissipated in each resistor is going to halve. So we're going to get half the power dissipated here from the circuit and half the power dissipated here from the circuit. Whereas in the first situation, the full power is dissipated through that one resistor. So each resistor is going to dissipate half. So it's P over 2. However, because we now have two components and each one has a voltage, an energy, like takes power. Um, it's going to discharge the cell twice as fast. So it's going to be uh, 2 times the discharge time. I do apologise. I've just said that wrong. Okay, let me. I've ticked the right one, but I've actually said the opposite of the answer. So the power dissipated in each resistor is in fact correct. It's the power in the circuit divided by 2 because it's sharing the dissipated power. It's dissipating half the energy in a certain amount of time, if you like. So um, the cell is going to take twice as long to discharge because each one is now dissipating half the amount of energy. So the energy is going to last twice as long in each cell. Apologies for that. So it's that one. So it's D. Okay. Question 34. We've got 2 wires and they're both carrying currents in the same direction. So they're creating their own magnetic field around them. So we're going to use the right hand thumb rule, right hand grip rule, and we'll be able to see that the field around this one is traveling, what's that, anti-clockwise, as is the field around this one. It's traveling, oh, sorry, I've drawn the arrow wrong that way, anti-clockwise as well. Okay, so we can see that if I was to branch this out a little bit, like this, eventually the fields would meet up, because what you'd get is this, and this, and eventually they get so close that they meet up. So the fields add together. When they add together, they attract. Okay, if they're adding together, the wires will attract. If they are not adding together, then the wires will repel. So we've got an attractive force and attractive force, so it's either A or C. But according to Newton's third law, if we have an attraction from this wire on the second wire, then we have an equal and opposite attracting force on the second wire from the first wire. So this is Newton's third law, which is true in this case. So it's A. And then question 35 is a vectors trig question. We have a plane that has a side wind. I'm not sure what you call that. A side wind, possibly, of 7.5, and a 42 thrust. Okay, and then what it's doing is it's actually changing its direction so that the 42 is moving to an angle to combat this this side wind. So the 42 is going into an angle like this. So what they're asking us to find out is what angle has it turned through? Okay, so I'll draw this in red. So what we can see is this is the starting off vector, if you like, bearing, and it's moved through an angle theta to 42, and it's got a horizontal component of 7.5, and we need to find theta. So we know the opposite, we know the hypotenuse, we don't know the adjacent, so I'm going to use sine. So we would say sine theta equals 7.5 over 42. So to find theta, it's sine to the -1, 7.5 over 42, and we just look for that in the answer. It's B.